Welcome to part 2 of our radicals and rational expressions video. And in this lesson, we are going to focus on rationalizing denominators. So a couple of learning targets for you there at the top. And one of the main things in this lesson that you need to take away is how to find the simplest form of a radical expression. And when you have an expression that has square roots in it, you will often have directions that say write the radical in simplest form or write the rational expression in simplest form. And that means it cannot contain a radical in the denominator. That's the biggest takeaway from this lesson is you need to learn how to rationalize denominators. And rationalizing the denominator will get rid of the radical or the square root in the denominator. So sometimes we're going to have a denominator that just has a single term, and when we have one of those, we simply multiply the entire expression by the denominator over itself, and that denominator over itself is a fraction equal to 1, so it's an equivalent fraction. If we have a denominator that has the sum or even the difference of a rational and an irrational term, we're going to multiply both the top and the bottom, the numerator and denominator, by the conjugate of the denominator, and I will explain that in the next slide. So here are two examples. The first one, we need to be able to simplify this fraction, this rational expression, and it has a square root in the denominator. So the only thing that needs to be simplified here, there's nothing we can cancel. So the only thing to simplify is the radical in the denominator. And there is only one square root, so what we're going to do is we're going to multiply the top and bottom by a fraction that contains that square root. So we're going to multiply top by square root of 10 and the bottom by the square root of 10, which will give us an equivalent fraction. We're not changing the value. We're simply rationalizing the denominator is what that's called. So now using our rules of exponents that we learned, we're going to go ahead and multiply the two radicals on the top together. 3 times 10 gives us the square root of 30. And then on the bottom, we'll have the square root of 10 times the square root of 10, which is just 10, or the square root of 100, which is 10. And that will give us 10 times 3, which is 30. Okay? And the very last step, remember, if you have numbers outside the radical, you can reduce your fraction. So 2 goes into 30 15 times, and that is our final answer. Now on the right-hand side, we do have a real component and an irrational component. So for this one, we need to first figure out what the conjugate is. And the conjugate is the exact same term, but just change the sign. So the conjugate of 1 plus the square root of 5 is 1 minus the square root of 5. So what we're going to do here is we're going to multiply both the top and the bottom of the fraction, the numerator and denominator, by that conjugate. So we have rewritten the fraction, multiplying by 1 minus square root of 5 on the top and the bottom. And a couple of things I might need to throw in here. On the bottom, when we multiply, these are called binomials. That was a really bad parenthesis there. These are binomials, and we need to use what's called FOIL. Hopefully you remember from previous coursework, when you're multiplying binomials, you use the method called FOIL, which stands for first, outside, inside, last. And then in the numerator, we're going to be using the distributive property and just multiplying both terms by the number that's outside. So when we do that, let's move down a little bit here. When I multiply the numerator, I get 4 minus 4 square roots of 5. Now a bunch of steps are skipped here, so I'm going to go ahead and write these in for you. When we multiply our first terms, 1 times 1 is 1. I'll just do that on the side here. Our outside term is negative square root 5. It's 1 times minus square root 5. Inside is 1 times positive square root 5. The outside and inside term by design will always drop out. They will always add to 0. That's what rationalizing the denominator does. Okay, it makes those irrational terms drop out. And then our last term is a positive square root 5 times a negative square root 5, which is minus the square root of 25. And we know that the principal square root of 25 is just 5. So we have 1 minus 5, which is where this negative 4 comes from. So our last thing we need to do to simplify this, we have 3 4's in here. So we're going to divide each term by -4 so that we can get a +1 denominator. And then what's going to happen is these two terms are going to switch positions. So we're going to have a positive square root of 5 minus 1 all over 1. Okay, so if you didn't see that, if I need to maybe write that out, if we divide 4 by -4, we get -1, and then we have plus, this 4 drops out, the square root of 5, which is the exact same thing, just written in a different order as what the answer is. So here are two for you to try, very similar to the last slide, excuse me. Go ahead and pause the video and give these two a try. All right, so this slide has lots of words. You have the words all written out for you, so I just wanted to go a little bit at a time. We're at the point now where we're going to learn about more than just square roots. We talked in class about square roots, and a square root maybe being like a jail cell where you need a buddy to get out. Well, we're going to expand that now to cubed roots, fourth roots, fifth roots, and so on. And square root functions are the inverse of squaring functions. So cubed roots are the inverse of a cubing function, and likewise for every other power. So for example, suppose we have this equation, a cubed equals 8. In order to solve that for a, we need to figure out what number raised to the third power is equal to 8. Well, you should recognize that 2 to the third power is 8. So we say that 2 is the cube root of 8, or if we were to solve that, a would equal 2, because 2 to the third power is 8. So in general, we can say that the nth root of a, and this is how we write that symbolically, the nth root of a is a number that when you raise it to the nth power will give you the radicand a. So n is called the index. We also sometimes call that the root number, and it's always a positive integer. And it's greater than 2. When it's 2, we generally don't write it for a square root, but if it's something higher than 2, then we'll write that index in there symbolically. Okay, so radical expressions can also be written without using the radical symbol. We will be converting back and forth. The one on the left is called exponential notation, and the one on the right is called radical form or radical notation. So you're going to be converting back and forth between these. So notice if n is 2, if this is a square root, that's the same as a to the 1/2 power. And I know we've already talked about that in class, so that's just a little bit of a review for you. We can also expand this out and have rational exponents that have a numerator other than 1. We can have things greater than 1. So let's just say it's an unknown value m. So we could have some base value to a fractional exponent. And if we were to write that in radical form, so again, here's exponential form. Radical form, remember the denominator is the index or root number. And then we can either put the exponent, the numerator here, outside of the radical, or we can put it inside the radical with the base number, with that radicand. Whichever way is easier for you to simplify, they mean the same thing. Usually I think you'll find that if you take the root of the number first and then raise it to an exponent, it's going to be easier, because otherwise you're going to get very large numbers under your radical. So let's look at some examples. Letter A says find the fifth root of -32. One thing to notice, 5 is an odd number, so we would never get a negative value under the radical if we have an even exponent or an even index. So we know our answer will be negative. So what number times itself 5 times will give us a 32? Well, the fifth root of -32 is -2. And that is true because -2 raised to the fifth power gives us -32. Okay, if we were to write that in exponential form, that would be, we could say, well, here's the exponential form right here. This would be -32 in parentheses to the 1/5 power. If we wanted to write that in exponential form, that's what that would look like. Okay, over on letter B, we are looking for the cubed root of this thing under the radical, and we're going to take the opposite of that in the end. So our answer in the end will be negative. Well, again, everything under here we're doing a cubed root, okay? So what we can do is break the numerator and denominator into separate cubed roots, and we can even break the numerator into two separate cubed roots. When we do that, we find that in the numerator, the cubed root of 8, I have my answer somewhere in here, I just need to find it, there it is. The cubed root of 8 is 2, and the cubed root of x to the 6th. I probably need to write this one out to make sure that it's clear. Remember, we need 3 buddies to get out of jail this time. So we want something to the 3rd power. So we want a power of x raised to the 3rd power. And remember, we're using our power rule, so this has to be a 2 because they're multiplied. So that's where this squared comes from. Okay, because we have an index of 3, we want that exponent right there to be a 3. And 125, the cubed root of that is 5. So our final answer is negative 2x squared over 5. Letter C, write 343 to the 2/3 power in radical form, and then simplify it. Well, this one, in radical form, remember the denominator is the index. That's what goes on the shelf of the radical. And then the 2 can either go on the inside of the radical or the outside. I generally will put it on the outside. And you can do whichever you please. You'll see that it's going to be a lot easier to put it on the outside first, because if we square this number, it's going to be very, very large, and you won't recognize what the cubed root of that is. So I would suggest putting the numerator on the outside of the radical as a general practice. And then the cubed root of 343, if you don't recognize that one, and I don't expect that you will, on your calculator you can take 343 and then use your caret key, and then you can go parenthesis 1, divide 3, closed parenthesis, and enter, and it will give you 7 on your calculator. Okay? If you have trouble finding that on your calculator, ask me in class and I'll show you how to do that. So we're not quite done. We know that the cubed root of 343 is 7, but then remember we have to square our answer. So the actual answer is 49. Letter D, we're going backwards. We have a radical expression and we want to write it using exponential form as a rational exponent. I will probably more commonly say write that in exponential form. So again, our index is 7, exponent or numerator is 2, and the 4 just stays there, right? So we have, first of all, we have 4 over a to the 2/7, okay? And we can write, remember this is in the denominator, so one of our rules says that we could put that in the numerator and make it negative. So we could write that as 4a to the minus 2/7, and that would be exponential form. Generally, we don't like to have negative exponents, so really I would rather have what you have on the left-hand side there than to make a negative exponent. Here are 3 for you to try, very similar to the last slide, so pause the video, try those on your own, and we can talk about those in class. Our last concept here in this video is simplifying rational exponents. So what happens when we have multiple exponents in our multiple fractional exponents? And so what we're going to do here is we're going to go ahead and we're going to multiply the number parts together. 2 times 3 is 6 and 6 times 5 is 30. A common mistake that students make is they'll think that this 3/4 also goes with the 2. But notice it's only with the x. Now if we had an exponent outside the parenthesis, that would also go with the number inside with that coefficient. But each of these coefficients do not have exponents. Their exponent is 1, so we can just multiply those numbers together. Then we have x to the 3/4 and x to the 1/5. Well, what do we do when we have the same base with different exponents? Well, we add those exponents, right? So now you have to remember how to add fractions. So we have x to the 3/4 plus 1/5, but we can't add those unless we have common denominators. Our denominator would be 20, so we're going to have 15/20 plus 4/20, and that gives us 19/20. So 30 times x to the 19 over 20. Not a pretty answer, but that's what we get. Over on the right-hand side, we have a negative 1/2 exponent. So to simplify this one, the first thing I would do is to go ahead and take care of that negative exponent. And what that does is it takes the reciprocal of that whole fraction. Another way of dealing with that, it's 1 over 16 over 9, which means 1 multiplied by 9 over 16 when you change that division to multiplication. So it really just flips the numerator and denominator and then change this to a positive. Okay? If you don't understand that, please ask me in class. I'd be happy to show you that and clarify it. So now what did we say that the 1/2 power was? This index of 2 means it's a square root, and the power is 1. So it's everything to the first power, but take the square root. So what we're going to do is we're going to take the square root of the whole fraction, which means we can take the square root independently of the numerator and denominator, and those are nice perfect square numbers, so we end up with 3/4. Here's your lesson check, couple of problems for you to try. Have those done before you come to class tomorrow. We'll see you next time.